Alright, so we've done the first 6 problems. No guarantees as to doing 3 at a time the whole time, but we have 7 next. So let's start there and see how far we get. Okay, so zoom in a little bit. Number 7 asks, what is the equation of a horizontal line with y-intercept 4 in polar coordinates? So that's kind of wordy, but we're basically asking, what form does this take in polar coordinates? And again, you know how I like to say that some equations look very nice in rectangular coordinates, and some equations look very nice in polar coordinates. You know, horizontal lines look very nice in rectangular coordinates because rectangular coordinates involve lots of straight lines. Polar coordinates involve circles. So we can expect this is not going to look so nice in polar coordinates. This isn't too hard to do if you remember that in polar coordinates, y equals r sine theta. So, starting from y equals 4, we have r sine theta equals 4. Or r equals 4 cosecant theta, which is probably how I'll give you the option. And if you graph this on your calculator, you'll get a horizontal line. Now, keep in mind that I'm certainly free to ask you to find a horizontal line y equals a, and then r would end up being a cosecant theta. So what I might do in the multiple choice test is to use a parameter like a, as you might have noticed in problem 8. That way you can't quite so easily just punch it in your calculator and find out. You can still use your calculator to build a conjecture, to test your ideas, but it makes it a little more involved, a little more pencil and paper. But anyway, this is all I was looking for number 7. 8. We're going to convert the polar equation, r equals a minus a cosine theta, into rectangular coordinates. Now something to keep in mind is we may very well not end up with a y equals f of x. And there are some reasons why. Consider equations of polar coordinates, such as r equals 3, which is a circle. There's no way of solving for y for a circle. A circle is not a function of x in the xy plane. Neither are any of the other weird things we've seen, like the figure eights or the limicons or the roses. All of those can't be expressed as functions of x anyway. So we're just looking for a relationship between x and y here. Again, we've got to remember that r is the square root of x squared plus y squared, and we're also going to recall that x over r is cosine theta, and y over r is sine theta. Okay, because these are the ways we tend to use them when we're converting from polar to rectangular. So let's start out. We have r equals a minus a x over r. And a is just a parameter. Now, if we multiply through by r, we'll have r squared equals ar minus ax. And not really sure. You can go various ways here, but at this point you could directly substitute if you wanted to. X squared plus y squared equals a square root x squared plus y squared minus x. I mean, this is fine. You could work on cleaning it up, but you know it's questionable how far you'll get. So, I mean, as far as I'm concerned, this is fine. You're not going to be able to graph this in rectangular coordinates anyway, so you can stop here. All right, number 9. We're asked to find the area between the x-axis and the graph of a polar function. We're given this polar function. Right? And so let's look at the graph. Again, I fully expect you'll have your graphing calculators with you. Nothing wrong with using them. So let's go to polar mode. Make sure you're in radians, of course. I'm also going to clear what I have in there already. And let's put in 1 minus sine theta and see what we get. So it's not a very good picture, so I'm going to zoom in. Alright, so notice we have one of these lemicons sort of symmetric on the y-axis. And we have these two pieces that are between the x-axis and the graph. In fact, I'm even going to zoom in a bit more, just for a little better picture. Alright, so we're concerned with these two pieces. Let's make a sketch on our piece of paper. Right. So what we need to know are our limits of integration. Now it's symmetrical about the y-axis, so we only have to worry about this part. Okay, we could do this part and then just double it. So initially, when theta is 0, we have 1. Okay, and then so this is 1 comma 0. This being theta. Now, as theta increases, sine increases to 1, meaning that this increases to 0. So we would expect this to move from 0 to here, this point being 0 comma pi over 2. And when you're doing this, again, make use of your graphing utility. So if I go to my window here, and I go from 0 to pi divided by 2, because that's what I think my limits are, I can graph that, and yeah, it's only that first part. So that really reassures me that I've got my limits right. Okay, so those are my limits of integration. So my integral is 1/2, again, alpha to beta of r squared of theta, d theta, which in this case is 1/2 0 to pi over 2, although I'm going to double it, so it'll be a 1. And I'll have 1 minus sine theta squared. Alright, d theta. So let's see, that's 0 to pi over 2. We can multiply this out. It's 1 minus 2 sine theta plus sine squared theta d theta. Using an identity, 1 minus 2 sine theta plus 1/2 1 minus cosine 2 theta d theta. And integrating theta minus plus 2 cosine theta plus 1/2 theta, let's see, minus 1/2 sine 2 theta from 0 to pi over 2. Now there are a couple of things to notice here. Let's simplify first. So theta plus 2 cosine theta plus theta over 2 minus 1/4 sine 2 theta. All right. This looks long and cumbersome, but it's not so bad actually because of the pi over 2. So we have 3 theta over 2 plus 2 cosine theta minus 1/4 sine 2 theta, right, from 0 to pi over 2. When you plug in pi over 2, you'll get 3 pi over 2 over 2 plus 0 minus 0, because this is 2 times pi over 2, minus, you plug in 0, you'll get 0 plus 2 minus 0. So that leaves us with what here? 3 pi over 4 minus 2 as an answer to our problem, as the area of that part of the graph between the curve and the x-axis. And that's problem 9.